Hello everyone. So welcome back to part 2 of the lecture 4, which is on support vector machines. So in the last lecture, we looked at support vector machines in particular, and we looked at the formulation of support vector machines, right? So this was basically the summary of the first part of lecture 4. And the summary is basically, I'll just kind of recap the summary, right? So the summary is basically simple. So the kind of main assumption of this lecture is that the data is linearly separable, right? So because the data is linearly separable, that means that there exists a separating hyperplane, right? Which is this one. There's a separating hyperplane. So there exists a separating hyperplane, which is W transpose X plus B equal to 0, such that it can completely separate the training and the test. It can separate the two classes, right? In the case of binary classification. So the goal of support vector machines is that, okay, so given this assumption of linear separability, there are potentially multiple possible separating hyperplanes, right? So the goal of support vector machines is to be able to find the separating hyperplane such that the margin, which is denoted by basically the distance from, say, the point to the separating hyperplane, right? Or you can also view it as the distance between the two parallel lines which form the closest points essentially on the both the positive and the negative classes, right? So essentially you can either call this distance the norm of 1 over the norm of W. So sorry, I'll just make this kind of a little bit more precise. So this is, sorry. So this is the norm of 1 over the norm of W. Okay, so this is the distance between the 2 points, right? So we want to maximize this norm, right? Subject to the constraints that all of my points, right? These are my positive points, right? So basically all my positive points and all my negative points, right, basically lie on the two sides of this, right? So essentially the way you can write this is you can maximize the distance, which is the 1 over the norm W, subject to the constraints that for all I, y of I multiplied by W transpose Xi plus B, right? This quantity should be greater than or equal to, greater than or equal to 1, right? So if it is positive, right, this is the positive side. So it is positive, then all my positive instances should lie on this side of the line. So this line is W transpose X plus B equal to 1. So it should lie on this side of the line, right? Should lie above. And if it's negative, right, if yi is negative, then W transpose X plus B. So this line is W transpose X plus B equal to minus 1. So this region is W transpose X plus B less than equal to minus 1, right? And this region is W transpose X plus B greater than equal to 1. So essentially this is the way you can actually kind of pose this constraint optimization problem. So this is what we saw in the first part, right? So I just wanted to give a very quick recap. So we saw the way of basically kind of putting all of this together. Okay, so I think two questions that we look at. So we won't answer this question right now. We'll answer this question in lecture 6 on how to deal with non-separable data. Okay, but in this part we'll actually do two things. We'll first kind of study various extensions of multi-class SVM. So this is called multi-class SVM. So far we saw the kind of way of formulating an SVM when is binary classification, right? But now we shall look at extensions of multi-class classification, right? Towards the end of this part, I will actually also go through a demo. So this will be a Python demo of actually showcasing exactly support vector machines. We look at linearly separable data. We look at why support vector machines actually finds this kind of maximizes the margin, right? And we'll actually see a demo of that. And I'll actually also contrast this with perceptrons. So in the last class, we actually saw Perceptron. Towards the end, we saw a demo of Perceptron, right? So we saw that Perceptron actually does not look at the margin, and we'll also, in this demo, we'll also contrast Perceptron with SVM on how SVM actually maximizes the margin, so it actually focuses more on generalization compared to Perceptron. Okay. So if the data is not linearly separable, then we can do higher order polynomials. So this we have seen actually in the case of linear regression, but we have also seen this in the case of perceptron, right? So the idea is very, very simple. I won't actually spend time on this for support vector machines, but the idea is the same as perceptron, right? So we can come up with these higher order polynomial features like the square features, the cube features, and so on, right? And I can basically look at a linear classification on these polynomial features. Okay. The other way of dealing with non-linear separability. Okay, so the first case when it's higher order features means the data is inherently separable, just that it is not linearly separable, right? So that means that we need in some sense some higher order features. So for example, if my data actually lies something like this, right? So this is my plus classes, and then these are all my negative classes, right? So if my data really lies something like this and my separating hyperplane is a circle, this data is separable, right? So this is separable, but it's not linearly separable, okay? But in some sense, the relaxation of constraints really makes sense if the data inherently is not separable, right? So imagine you have a scenario like this where I have my positive classes, right? And I have my negative classes. But I have some positive classes that probably lie over here as well, right? Close to the boundary. And I have some negative classes that lie close to the boundary. So in this case, essentially the data, I mean, you cannot find a single linear or even higher order probably kind of separating hyperplane that exactly separates this, right? So maybe what I need to do over there is that I can say that, all right, I will try to, you know, fit a line something like this, or maybe a better line. Yeah, so maybe this is the line, right? And then I maybe account for a certain slack that I'm fine if my, you know, if I make an error with a certain amount of slack on both sides. Okay, so this is what we'll actually look at, relaxing the constraints and looking at slack variables later on in further lectures of SVM. Okay. So now we'll actually focus on multi-class classification. Okay, so multi-class classification, I have my ones, I have my twos, and I have my threes, right? So how do I, so in some sense, I want to be able to kind of fit separating hyperplanes which look something like this, right? So there are actually multiple ways of doing this. So we'll see all of these multiple ways. So one approach is one versus all SVMs, right? Which is, I think, most intuitive. What you do is that I take my positive classes, right? And I'm separating, so in some sense, suppose this is one, right? So I'll call this is class one positive, right? And then this is class one negative, and similarly, this is class one negative, right? So that means that this region, this hyperplane, right, would be class one separating hyperplane. Okay, I do the same for class 2. So this is class 2, maybe this is the class 2 separating hyperplane, right? So actually this is kind of marked in green, so this is class 2 separating hyperplane. Okay, so actually what I'll do is I'll kind of erase this line that I've drawn because I think it's kind of evident from the color, right? So from the color you see that this is class 1 because it's in orange, this is class 2 separating hyperplane, and similarly this is the class 3 separating hyperplane. Okay, so the way this works is that I do 3 multi-class classification problems. I mean 3 binary classification problems, right? So the first is class 1 versus not class 1, right? So not class 1 is class 2, class 3. Right, so I train one model which is class 1 versus not class 1, right? And that is this orange model, right? This one. So I get one separating hyperplane. Then I train a class 2 model which is class 2 versus not class 2. right? And this is this separating hyperplane, right? And then I have my class 3 model, and this is my class 3 model, the red hyperplane, right, which separates class 3 versus not class 3. So I have all of these 3 hyperplanes. So with this, I know that this region is class 3, this region is class 1, and this region is class 2. Right, so that's exactly what is kind of plotted over here. So this is class 1, this is class 3, this is class 2, right? Okay, but there is still some ambiguity. So in particular, the ambiguity is that this region, right, is essentially none of the classes, right? Because we know that this region on this side is class 3, right? So we know that this side is not class 3, right? So this side is not class 3. Similarly, this side is not class 2, right? And this side is not class, this side is not class 1, and this side is not class 2. So this region that I have in the middle essentially is none of the classes, right? And another set of points which is ambiguous is the points over here, right? Because if you take, for example, the points over here that are marked with a plus, right? This one we know that this one intersects both class 1 and class 2, right? So similarly, this region actually is class 2 and class 3, right? And this is class 1 and 2. So if we just look at the output of the classification, right, and just use the class hypothesis, okay, then we only actually get a kind of sure shot classification on this region, right, this region and this region, right? So basically the region that I've kind of tried to highlight over here, but the rest of the regions actually are ambiguous, okay? So this is what actually this kind of tries to go over here. So the idea is that I have a classifier, okay? So I try to classify each label versus the remaining labels. So it's one versus all, right? One versus rest, really, right? So I take the label and all the remaining labels and I try to do a binary classification, right? So essentially the idea is that I have something like this, right? So I have for each class, I have a WK transpose X plus BK, right? And then I can actually classify this by taking the K prime equal to R max. Okay. So the only drawbacks here, the drawback here is that we require learning L classifiers, right? So because it's one versus rest, basically the kind of compute increases L times given L number of labels, okay? But still, we need to address this issue, right? So if we just use the class output, it obviously doesn't make sense, okay? So there is a slightly better way of doing it, and the better way of doing it is actually to classify it based on the points that are classified by the highest value of W transpose X plus B. So I don't just care about the what the classifier says in terms of the discrete label, right? Because a discrete label can be confusing, but rather I use the score, right? So note that, for example, this region over here, right? So if I take this region, it is actually closer to, this is actually closer to 3 than 1, right? Similarly, this is actually closer to 1 compared to 3, right? So maybe I'll just call these are actually 3 as well, right? Similarly, these are 1, right? Similarly, these are 1, right? And these are 2, right? And these are 2, these are 3. So we see that we have actually these kind of side regions that are there, all of these side regions, right? We have kind of removed the ambiguity here. But what about this central region, right? Because if you just look at the class label, the central region actually belongs to none of the classes. But again, if you look at the highest value of W transpose X plus B, well, you can do the same, right? Because this region is actually closer to 1 compared to the other two. So I would classify this as 1. I would similarly classify this as 3, and I would classify this as 2. Okay. So with this, we see that if we actually classify the regions based on the score of W transpose X plus B, I can actually classify the entire region, right? And this is actually what is done in practice. So in practice, you don't actually use the output of the classifier, but you take the highest value of W transpose X plus B, which is also called the score. And there's a score of each class, right? So I basically score each class because you recall, I actually have WK. So each of my K, for each of my K, I have a WK and a BK, right? So actually the notation I've used is so I'll just use a comparable notation over here. So this is actually this is WK transpose X plus BK, right? And I do a argmax over K of this score, and I choose the best one, right? So this is exactly what this essentially kind of thing is showing. Okay. All right. So now there is one more way of doing it. It's not very kind of commonly used because of the issues, as you will see, right? But another possible alternative strategy is to actually construct a classifier based on all possible pairs of labels, right? So what I mean by all possible pairs of labels here is that I actually take, given my classes 1, 2 until k, I take every possible pair. So I will train a classifier on 1 versus 2, right? 1 versus 3, 1 versus 4 until 1 versus k, right? Similarly, I will do 2 versus 3, right, until 2 versus k, right, and so on and so forth, right? So as you can see, there are actually there are k labels, there are k choose 2, right? Or in this notation, if there are L labels, it's L choose 2, right? So there are L choose 2 possible number of classifiers, right? And each of them only sees a fraction of the data, right? So I think the issue, there are actually two drawbacks here. Okay, the first drawback is that we can have some overfitting, right? Because we do not have a significant amount of data for each class, right? So we have, imagine if I have my total data set is of size n, right? I roughly have essentially n per L on average, n per L instances per label, right? So there are essentially, I'm looking at 2n plus 2n over L data points to actually get my classifier. So I'm looking at significantly lesser amount of data, whereas over here, I'm actually getting a much better picture because I'm looking at all L data points. Okay, one more issue which is basically kind of obvious is that there are L choose 2, right, which is actually pretty large compared to just L, right? So L choose 2 is actually L choose 2 is actually L into L minus 1 divided by 2, right? So this is actually quadratic in L as opposed to linear in L. Okay, so the issue is also that it is the second issue that it's much more computationally expensive. Okay, but never mind. Just for kind of completeness, right? You can see that you get a plot something like this, right? So if I do, for example, this classifier that I have over here is 1 versus 3, right? So I have 1 versus 3 being shown over here, and this one is 3 versus 2, right? So this region is 3 versus 2. This is 1 versus 3, right? And this that I have over here is actually 1 versus 2, right? 3 versus 2. Yeah. So I have, so in some sense, because it's 3, I still have 3 because 3 choose 2 is 3. But immediately as you have 4, you will see that instead of having 4 in the case of 1 versus rest, now I have 4 choose 2, which is actually 6, right? So I have 6 kind of separating hyperplanes in the case of 4, when the case of number of labels is 4. Okay. Anyway, so this is the kind of major crux of multi-class classification. Okay, so with this we will actually end the way we can deal with multi-class classification. So as you saw with SVMs, the kind of simplest strategy of dealing with multi-class classification is just to extend binary classification and look at 1 versus rest is the kind of the most common way of doing it, but you could also do 1 versus 1, right? Or basically pairwise SVMs. Okay, so with this, let me actually bring up a demo of SVM. Okay, So again, I'd like to acknowledge that I use this basically Python data science handbook demo for SVM. So it was pretty straightforward to actually use this demo and actually set this up. I kind of modified it a little bit, but for the most parts, it's basically kind of built on top of this, right? So it's very, very intuitive. So that's the reason I basically chose this demo. Okay, so what I'm doing over here, I'll actually put up the code for you to see afterwards as well. What I'm doing is that I'm just importing a bunch of libraries here. Then I'm actually looking at, I'm basically kind of plotting a data set. Right? So this is a synthetic data set, and the synthetic data set is completely separable. So these are the red classes. I mean the red instances, which is one class, and the yellow instances is the other class. So the two classes are completely linearly separable. Okay. So then what I've done is that you can actually draw multiple separating hyperplanes, right? So again, the cross ones that over here are actually kind of test data points. So ignore the cross ones. If I just have these circle points over here, right? Each of these three separating hyperplanes actually separates this. But as you saw in Perceptron as well, right? If you look at this separating hyperplane, and if I were to get this yellow test point, right? This separating hyperplane would actually incorrectly classify this yellow test point at test, even though the training accuracy would be perfect, right? And in contrast, if I have this separating hyperplane and I have this red cross point in test, right? Then this red cross point would get incorrectly classified in the case of the top hyperplane over here, right? This one. So the only one that actually makes sense is the kind of in the middle one, right? And this is in some sense the one that maximizes the margin. Okay, so we'll actually see this, right? We'll actually see that support vector machines does exactly that. And for that, I actually take my data set. So I formed my data set already. So I have X and Y as my data set, right? So I've already formed my data set. I can import SVC, which is scikit-learn support vector machine. I have a linear kernel. We have not seen kernel yet, but basically it means that it's just simple kind of a linear model, right? Which is what we have seen so far, right? And I do model.fit and I get my SVC. Okay, so this is my support vector. I have a simple function here that actually plots the decision function and decision boundaries, right? So I basically use this function here, and here we go, right? So this is the separating hyperplane, this line over here, and these two are actually the lines that fit the support vector machine. So these are parallel lines which are W transpose X plus B equal to 1. So once I learn my W and B, this line is W transpose X plus B equal to 0, right? These lines are W transpose X plus B equal to 1. As we saw in the class as well, this would exactly be the points where my support vectors or the closest training points to a decision boundary would actually lie, right? Imagine now if my points are actually closer, then you can imagine that my the region gets kind of shrunken, right? So I have these two basically much closer to each other than in that case. Okay, but nevertheless, I have this kind of very intuitive way of doing this, and these points are the support vectors, right? So I have three support vectors in this case. I actually look at the support vectors. So the first is 0.44, 3.15. So I believe the 0.44, 3.15 is this point, right? The second point is, sorry, I think the 0, yeah, that's correct, that's correct. So this is 0.44, 3.11. This point would be 2.33, 3.43, right? So both of these belong to the same class. And I think this is the third separating hyperplane, which is 2.06, 1.96, right? So it's just below the two lines. So this is the third one. This one is just below the line, so this is not actually a separating hyperplane. So only there are three separators in the the support vectors. So there are three support vectors in my in this data set. Okay. All right, so I think the support vector machine was fairly clear. On the same data set, I also plotted a perceptron just to basically showcase, right? So perceptron, instead of using our own code for perceptron like how I did last time, I used sklearn's perceptron, which is basically the same thing, right? And I fit this model on the perceptron, and then I plot this, right? And lo and behold, this is exactly what we see, right? So perceptron over here does not maximize the margin. And in fact, in this case, it actually got this region which is very, very close to the yellow, right? And this is not good from a generalization perspective. So there you go, right? So you contrast this set of plots for perceptron versus support vector machines, right? And it's the same data set, but just that the decision boundaries are very, very different. Though both are perfect classifiers on the training set, right? They are still very, very different. And in some sense, this one makes the most sense from a generalization perspective. Okay. So thank you so much. This ends the support vector machines class. And in the next lecture, this ends the simplest kind of version of support vector machines, which is just linearly separable. The next lecture, we'll actually look at the duality of support vector machines, which will give us the ammunition to actually go into kernel machines. Okay? So the kernel formulation of support vector machines, which basically would be the first kind of non-linear classifiers. We would still assume that the data is separable. Okay, and then in lecture 6, we would handle these separability assumptions. So we would look at basically relaxations and look at slack variables, right? And then we would see how we can actually handle basically non-separable data with support vector machines, right? And then in lecture 6, we'll conclude support vector machines, and then in future lectures, we look at other topics of machine learning classifiers. Okay, thank you so much, and hope you enjoyed this lecture.